So welcome back, everybody, and I hope you had a great Easter break. We are going to begin with a new topic now, and this topic is about machine learning methods and quantum machine learning. So today I'm going to give you a quick introduction to a basic overview of quantum machine learning methods, but then we are going to dive into a classical machine learning method, which is called support vector machines. And this is going to serve as a bridge towards quantum support vector machines. Now, support vector machines form what is called a classical machine learning method, a deep learning revolution methods. So these were methods which are essentially based on linear algebra and optimization methods. So it's an optimization of a function with constraints. And I'm going to go through the basic mathematics of these methods, because then the transition to the quantum support vector machines is hopefully a little bit easier. So the main bulk of the lecture today, besides the introduction to quantum machine learning methods, will rotate about the basic mathematics of support vector machines. Now, support vector machines also have another name. They're often called kernel methods. And you will see that in the applications in the lectures today and also partly next week. They're also called exponential machines. So the typical thing then in this kind of machine learning methods is that you map an input to an abstract feature space, and then you retrieve the output by projection to a smaller space of observables. And the projection includes a large number of parameters, which are then fitted through a basic optimization machinery. Now, for the classical support vector machines, I do actually have extensive lecture notes, but you can also find lots of notes on these. There is also a recent textbook which you can download for free if you're on an IP address of your universities. If you don't have it, if you cannot access it, just let me know and I will send you the PDF. And this is a book by Claudio Conti. And in the lectures today, it's essentially sections from 1.5 to 1.10, which are the most relevant ones. And I will use this one in connection with the lecture next week as well. So if you then look at the classical machine learning, what we have is supervised learning, which is the case for support vector machines, as we will see today. And we will focus firstly on classification problems, but they can also be extended to regression problems where you are fitting a continuous function. They are less used for unsupervised learning. Actually, I don't know any examples. And the other class of machine learning is reinforcement learning, which we will not touch upon. This should actually have been a bullet point 3. So this is a typo here. So the typical workflow is that you have a data, you have a model which you train, and based on that one, you make a prediction. Then, if you look at quantum machine learning, so quantum machine learning, as we have seen now, and quantum computing in general, integrates quantum computing with machine learning algorithms to exploit quantum advantages. So one of these big advantages is that we have a high-dimensional Hilbert space, which allows us to represent many more features than a classical machine learning algorithm. We can use, as we have been discussing earlier, quantum parallelism for faster computations. And then we can have quantum entanglement for a richer data encoding. So this is one of the big benefits of the quantum machine learning based on quantum mechanics. So just to have a kind of image, suppose you have an example of 100 qubits, and each of them can be in a state 0 and 1. That means that the total Hilbert space has a dimensionality of 2, that is your binary case, which we have now, to the power of number of qubits. So if we have 100 qubits, this is 2 to the power of 100, which then defines the dimensionality of the Hilbert space. So if you have d equal to 100, that corresponds roughly to 10 to the 30th number of states. And that is, as far as I've understood, much larger than the number of stars in the universe. So it's impressive that we have access to such quantum computers nowadays. Actually, many of the IBM machines actually offer more than 100 qubits. However, it's difficult to exploit all these states, as we have seen. The majority of the states are actually entangled. And if you look at large-scale entanglement, this is something which is hard to support when you interact with the classical world. So within the many inaccessible entangled states, the much more friendly product states, which we have looked at earlier, is something which gives us a much smaller dimensionality. So, however, without entanglement, then there are many benefits of quantum computing which we cannot use them. So the quantum benefits are, as we said, quantum parallelism, we have quantum entanglement, we have quantum interference. And as we discussed before the break, if we look at a discrete Fourier transform, the number of operations where n here is a number of states runs like n cubed. Actually, this should be n times log n, so there's a typo here. Whereas for the quantum Fourier transform, we can reduce this further. So if we have something like a million state for the discrete Fourier transform, we can reduce that one to 10,000 operations with a fast Fourier transform. And then with a quantum Fourier transform, we can reduce that down to 100. So there's a small typo here. I'm going to correct this one. Without entanglement, the quantum system is essentially equivalent to a classical one with the same number of parameters as you would get if you have a product state. The problem with the quantum systems which we have is that the entanglement requires normally that the system is isolated from the environment. Any interaction with the environment can destroy possibly the entanglement. And these circumstances make quantum computers expensive and hard to build. A further issue is that quantum measurements are probabilistic. So we actually need repeated, as you saw also in project 1, when you calculated the eigenvalues of a quantum mechanical system using the variational quantum eigensolver, is that you need a repeated set of measurements in order to get a certain confidence in the output. That means to reach a certain accuracy in estimating statistical quantities, such as a mean value, which in our case was the energy. For these reasons, the details of a specific implementation determine if a large-scale quantum computer is advantageous with respect to the classical counterpart. So the common wisdom is that if you have a task that is solved efficiently by a classical computer, that is, it scales polynomially typically, you do not need a quantum computer, which at best will also scale polynomially. So quantum computers are needed for those tasks that we cannot solve efficiently by a classical computer. And the accuracy in a quantum computer is also limited by uncertainties in the parameters, which are due to fabrication imperfections and tolerances. And this aspect becomes also progressively more critical as the number of qubits increases because of the resulting circuit complexity. Then there are some intrinsic limitations. And some of these limitations have to do with the fact that a quantum register is something which we cannot copy. This is something which we haven't discussed in these lectures. This is called the quantum no-cloning theorem. Or we cannot access the precise content of a quantum register without collapsing its state. That is, when we make our measurements, we typically collapse this to a final observation. So these kind of limitations, they actually hamper our quantum algorithms, but they also stimulate new research and new kinds of programming protocols. So what we are going to do today, besides these kind of discussions, general discussions, is actually to dive into support vector machines. And I actually wanted to go through these in some more detail so that you see the transition from a classical support vector machines to a quantum support vector machines. Now, whether a quantum support vector machine is going to be beneficial for a specific problem is not something which we can tell a priori. But I wanted to go through these basics of support vector machines before we go into the quantum variant of it, so that you see clearly the differences and where quantum can come in as a benefit. When we have discussed, after we have discussed quantum support vector machines, which will also be the topic for next week, we are going to start looking at the quantum neural networks. And if we get some time, we will also say something about quantum Boltzmann machines, which is another very interesting area of applications. So this is essentially the topic for the last 4 lectures, which we will have. And we will have the last lecture on May the 14th. We will also have lab on May 21st, for those of you who can. But the kind of plan now is to cover some of these basic quantum machine learning algorithms. So I'm going to switch over to the whiteboard pretty soon, and we're going to look at the mathematical details of the classical support vector machines. So let me switch to the whiteboard. And look at the basics of classical support vector machines. So let's look at the basic mathematics of these support vector machines. And let's take a very simple case. So what we're going to look at now is a data set which is characterized by 2 input parameters. So we have our data set, which has now 2 features. So we have a series of observations, and these features are now vectors x1, which is now a vector which contains an observation x1. So this is the vector. So the subscript here is the label of the vector. This is a specific observation, and it's x1 of 1, etc., up to an x1 of n-1 observations or features which we have. So this could, for instance, be a set of patients, and we have another feature as well. So these are features of could be a feature of a specific illness if we want to. So this is another feature, and then we have observations. So each observation could be a patient, and then we are looking at specific features. So if you're doing tumor research or cancer research, this could be the thickness of the cancer. That's one feature, and another feature could be the circumference of a tumor, just to give you an example here. So this would be a set of elements in these vectors, which are now the specific features which are being observed for a given set of patients. And in total, we have n-1 patients, and then we have the outputs. So we can think of the x's as the inputs, and each output is now given by a vector. So we have to put up transposed here because these are transposed vectors. And then we have observations here, y0, y1, up to yn-1. So we could now think of this in a very simple way as a data set where we have x1 on one axis and then we have x2 on the other axis. And then we have a set of observations, and here we have circles. So the circles correspond to a region which I'm going to call C2, where y of I is equal to -1. And then I have the crosses here, which now correspond to another set of observations. And I'm going to call this domain for C1, and that corresponds to y of I equal to +1. So we have 2 outputs. It is a binary case, so true, false, 0, 1. I chose to have it to be -1 and +1. And then what you could think of now is that there is a line here where we could, for example, say that y, this variable y, is exactly equal to 0. So what we would say then is that if y is larger than 0, then the outcome is given by region C1, which means that y of I is equal to +1. If y is less than 0, then we would say that we are in region C2 and y of I is equal to -1. So you could think of these as different types of features, and then we have a set of observations and outputs which now are the type true, false, -1, +1. So what we want now is to find a way to distinguish between these two classes. So this is a classification problem, the way we have written it here. So it's a classification problem. And support vector machines, if we now want to take a top-down view on it, is us being able to find a demarcation region so that we can actually separate two classes in one way or the other. In this case, it's pretty simple because we could just fit a straight line between the two classes. Now, what you know when you fit a straight line is that this straight line can have different tangents. So we can have tons of different lines which separate these two classes. So the question is, can we actually set up a method which is slightly better? And this is where support vector machines come in. And I'm going to give you the basic mathematical details of a support vector machine. So the task now is to find a way to separate these two classes so that we can make a prediction that if y is larger than 0, then the output should be +1. And if y is less than 0, the output should be -1. Let me know if there is something unclear here with the basic overarching idea behind the support vector machine. So if there are no questions, I'm going to proceed with the setup of the basic mathematical recipe for finding this demarcation. Okay, so let's continue. So what we want now is to, after we have made this definition, so y takes values, in our case, which are either -1 or +1. Then we are going to have a vector x of t, and I'm now going to write this in a simpler way. So suppose now that we have only this x1 and x2 here. And we have a set of observations. Now, we are going to define a variable w0, which is going to play the role of what we in machine learning call for a bias. But in our case, since we are fitting a straight line, this is something which we could also think of as an intercept. So we will make a model in terms of this vector x, which is given by y tilde as a function of this x. And this is going to have this w as a set of parameters multiplied by x plus w0. And if we write it out, this is simply going to be an unknown parameter, w1, multiplied with this feature x1, plus a unknown parameter, w2, multiplied with the feature input x2, plus this w0, which plays the role of an intercept. So what we are going to train now is a model where we are going to find these unknown parameters, w1, w2, and w0. And then when we now calculate a w of x here, if it's larger than 0, then the output is given by y equal to +1. The output belongs to this region, belongs to C1, which means y of I equal to +1. So y of I is one of the possible outcomes. And else, if it's less than 0, then it belongs to C2. Which then means that y of I is equal to -1. Okay, so let's continue a little bit. And we are going to say now that y, this model which we have trained, when that one is equal to 0, that defines the boundary. Actually, support vector machines are very popular machine learning algorithms. especially when you have smaller data sets, which you can handle by standard linear algebra methods. So the y of x equal to 0, when we've trained the model, that defines a specific boundary. So if we now make a plot here, we have defined a specific origin. So we have x1 here and x2. We have found this demarcation line, or the line which separates the two faces or the two domains. Then every point which we have on this line, so this is a point x of a, and that leads to y of x of a tilde equal to 0. We can have another point here, x of b, and that means that we have y x of b equal to 0. So these are all on the line. In this specific case, we have y less than 0. And in this domain, we have y larger than 0. So this is y tilde. And then we have now a point x here. And then when we have this point x, we would like to find out what is its region, which then gives us the value of y which we are interested in. So another thing to notice now is that if I take wt and multiply that with x of a minus x of b, and remember now that the full model has a plus w, but since I'm subtracting x of a, y of x of a, and x of b, w disappears. So we see that this one has to be equal to 0. This line which we have here, if we are looking at more than a two-dimensional case, this is normally called a decision surface. So let's just put up the name, decision surface. So in the example which we are going to look at here, we are simply looking at a case which is given by a two-dimensional problem, and then the demarcation surface or decision surface which we're looking after is given by a line. So this w, this vector w, which we have defined here, so we define this vector w, which now contains the parameters w1 and w2. So these are unknown parameters, which we're going to determine through the optimization. So w determines the orientation of the decision surface, or line in our case. So we are looking at a line here. And from a chosen reference. From a chosen reference. And in our case, the reference was the origo of this x1, x2 system. So what we have then is that we have a point on this decision, which is a decision surface, which then requires that this model should give us 0. And that is given by this wt of x plus w0. Now, we could easily fit this with a standard linear regression method. The only problem then with a linear regression method is that we could get an infinity of such lines which separate the two domains C1 and C2, which we are looking after. So let me just bring in some technicalities here. So I'm going to define a point where y tilde is exactly equal to 0. And I'm going to call this x perpendicular to, and you will see why I'm going to use this symbol perpendicular to from a geometric analysis of the problem. So this is now a type of variable which I will use now throughout the derivation of the method. So we are going to normalize this vector. So this is another technicality which I need to bring in. Normalize W. So this is going to be normalized in terms of, since these are vectors now, we need to take the inner product, and this is the norm 2 of a vector. And I will just use this symbol here for the norm 2. So when I normalize then, what that means is as follows. So when I look at this specific point, when we have a variable x, so let's now look at the same plot which we had before. So we have this decision line or decision surface. The x of t is now a point on the line. And this is my x of t, x perpendicular. And the reason for why it's perpendicular is that the vector w, in order to fulfill the condition that y tilde should be 0 here, y tilde of x perpendicular is equal to 0 here. That means that the vector w has to be orthogonal to the line. So that means that the vector could now have a length. So this is my vector w. I'm looking at a point up here. So this is any random point. And I want now to define that one in terms of this vector x perpendicular plus the norm of the vector which I have. So if I now look at the kind of model which I made, I'm going to have a w of t plus x is given by something. So let's now take a look at it, because if I now take and normalize my data set, so what I'm going to have is that wt of x, when I normalize it, and I require that this one is equal to, because this when y of x is equal to 0, this is going to lead to minus w divided by the norm here. And my point x is now going to be defined by x, the perpendicular point, plus an addition, which is going to be given by a constant delta. And this constant delta is now given by wt, the transpose, divided by the norm. This constant delta is actually given when we now use the fact that it is 0 on the line. This is now defined as y of x divided by the norm 2 of the vector w. So that means that I have a kind of recipe where I can now set up my given vector x in terms of this quantity here. So these are just manipulations of the equations which we have. And this quantity here is now given by y tilde of x, a given vector, divided by the norm of this vector. And the vector x is simply now us setting up a vector which then contains this delta quantity here. So these two vectors together, and this will actually be given by a w, the norm of it. And then we can construct the final x in terms of a vector which is orthogonal to the separation surface or separation line or decision surface, and a point here where the value of y tilde is exactly equal to 0, which is for that specific point. And we know that the y of x, the perpendicular one, is given by wt times x plus this w0. And we know that this one has to be equal to 0. So one thing which we could do now is to find these parameters, find w1, w0, and w2 by a simple optimization problem. And one way we could do that is simply now to set up the following. So assume now that we could define a cost function, which is the function we want to optimize in order to find the best parameters. It's also called the loss function. Sometimes it's called the risk function or the error function. We could now set up a optimization problem which contains a cost function, which now includes all misclassification points. And then we want to minimize all the misclassifications. So what we could do now, if we look at the problem which we have, is to do a kind of intermediate step or a kind of optimization problem. So the kind of optimization problem we could do now is to define a cost function, a cost or loss function, which contains all misclassifications. So we are training a model, and some of the points will be misclassified. And then we want to optimize the set of misclassifications which we are making. So which contains all misclassifications and suppose now that this is a set which we label as M. So let's call this a set M. And we want to minimize this one. And so we have defined such a cost function, and we want to minimize it. Minimize this specific function. So what we could do then is now to define such a cost function, which depends on the parameters W1 and W2. So W is a vector. And then we have this bias parameter in order to use the same naming which you would find in neural networks. Here, when we have a straight line, it just plays the role of an intercept. So in this case, what we could do now is to minimize a function which runs like this. So we have a sum over all the misclassified predictions. And then we multiply that with y of I. So we have a model where we have WT. And now you have to be a little bit careful here because x of I is a vector in principle. So when I write x of I, so y of I is the final output. And in our case, since we have chosen a binary type of problem, it can be plus or minus 1. But x of I can now include x1 and x2, these two features, and we will deal with x as a vector. So let me just mark this here, that this is a vector in principle. So it can be a vector. And then we have a plus W0 here. And we know that if y of I is equal to 1, then we have a misclassification. Classification if our model, so we have trained a model where these parameters W0 are less than 0. So if we have a misclassification, that means that we get a negative value here. We have 1 here, so that means that we get a negative value, and a minus 1, so that gives us a positive value. Else, if we have a y equal to 1 case, then we have the opposite case. If y of I is equal to 1. So if we have a misclassification then our model, which we have here, which is again the same. So what we are writing here is actually a function which is given by, so this cost function of C of W and W0 is the same as minus I of this set, which contains the misclassifications of y of I tilde. So y of I tilde is our model, actually. Now, if we now want to optimize, what we would do is then to take the derivatives. So we take the derivatives with respect to W0, and we put that one to 0. So we are setting up the gradients, and then we are going to perform, we could now use Newton's method and do a plain gradient descent with a fixed learning rate. And you will see in the programs which you have in the Jupyter notebook that you need to specify what the learning rate is. So you could set up a simple program here, because this one is something which we can easily calculate. So I, inside this set of misclassification of y of I, if I take that derivative, if I take the derivative with respect to W, so which in principle represents a vector now, this is now given by minus I, still in the set of misclassified predictions, multiplied with x of I. And x of I is a vector now. Just keep that in mind. So if you then want to perform or set up a very simple program, you could now have an update for the parameters, update with gradient descent. And this is one of the basic standard recipes which you would find in any machine learning algorithm. So we have the gradients, and that means that we can update the parameters by starting in an iterative way with a value at an iteration 0, which is just a guess. It could be just put to 0. And then we have an eta, which is a learning rate, where we can have different recipes for updating that as well as a function of number of iterations. Then we have the gradient here. And then we will do the same thing with a vector W, where we now update according to an initial value and multiply it with perhaps the same learning rate. And then we have the gradients here. So this would be one way to solve it. One of the problems, however, when we are dealing with this type of solutions is that this type of method can actually lead to different decision lines. Now, we don't want to have many possible decision lines, but we would rather like to have a well-defined region which we can use to say that here is where we are in either -1 or in the +1 case. So the standard way by which we normally develop the support vector machine calculations is to define something which is called a margin. So solving these equations which you see here can actually lead to different decision lines. So what we want to have is, however, something which we are going to call for a margin. And I'm going to label this as an M. So what does that mean? So let's look at this two-dimensional case with x1 and x2. We are going to have a set of observations which now live in this region C2, where y of I corresponds to -1, or as we have drawn them in the figure here, as circles. And then we are going to have the y of I equal to 1, which we draw as crosses. So these are the two classes of observations which we want to have. This could be another circle. And in this case, we have C1 with y of I equal to +1. Now we can find now a kind of demarcation where we find the point which is closest to a midline. So if you now look at this last observation here, and if we also look at this observation, then we can draw a midpoint line, or midline as it's often called, between these two. So this distance, if we can find this distance here, this distance is called the margin. And here on the decision line or decision surface, we have that y of x is exactly equal to 0. So this margin, which is going to define, so the distance between this the decision line or decision surface to the nearest lying point, this x, is going to define the support vectors. And this is the only data set which we need to take care of when we are setting up the final model for which we want to use to make predictions. So this margin is something which will now define more precisely the boundary between the two classes of observations. And support vector machines lead to a standard linear algebra method with the optimization problems incorporated, but where we now are going to optimize with a constraint. So what we want now is to find a margin which is going to give us the following. So we seek this margin. We seek a margin so that when I now take my model, which I had previously, my prediction, so my prediction is given by 1 divided by the norm of these vectors W, and this is multiplied by Wt of x of y plus this W0. This is my prediction. And when I now multiply my prediction, so let's put that one here. So this is what we called a y of I of x of I. This is multiplied with y of I, our data. And we want this one to be larger or equal to this margin. So if it's equal to the margin, then we are actually at the point. If it's larger, then we know that we are either in region C1 or in region C2. So we know in principle that when we take y of I, so this is y of I tilde, this is the kind of operation which we want to set up, and we are now going to have this one larger or equal than 0. This is what we did in the previous case. So if we now look at this equation which we have here, we can rewrite this equation by multiplying away the norm. So I can now set up y of I, multiply with Wt of x of I plus W0, going to be larger or equal than this number m, and then multiply with W and the norm of W. So what I can do now is to define m times W equal to 1. So I'm just scaling this margin m. And that means obviously that m, so this is just a way to scale it, is 1 divided by the norm of W. So that means that what we can do now is either to maximize the value of m, or we can minimize the norm with a given constraint. So the problem which we want to solve is of the following type. So we could minimize the norm with respect to the parameters W and W0. So we perform an optimization also with respect to W0 with a constraint and this constraint is that y of I multiplied with Wt of x of I plus W0 is larger or equal than 1. Alternatively, I could take and maximize m with the same type of constraint. So the correct prediction is obviously that this, if we are on this exactly on this line here, then the correct prediction would give us y of x equal to 0. Now, what we're going to do after the break here is to look at how we can rewrite this, since we now have a constraint in terms of an optimization problems with constraints. And that will also lead to an introduction of a Lagrangian. We are going to introduce Lagrangian multipliers in order to set up the final optimization problem, because we are having now an optimization problem with a given constraint, which is the problem which we have defined here. So a typical example which you could think of before we take a small break is an example of the following type. Sample 1 here. We could now have a function f of x1 of x2 equal to x1 minus x2 squared. And then we could have a constraint which runs like x1 larger or equal than 0 and x2 larger or equal than 0. So in this specific case, we would have two specific constraints. And then when we have this type of problems, it's common to actually use the machinery of a Lagrangian formalism and to introduce so-called Lagrangian multipliers. But let's take a small break before we proceed with that. So what we are going to do now is to develop the basic machinery for support vector machines. And we're also going to extend this to a transformation of the data points, particularly input values, using what is called a kernel transformation. And then we're going to set up the final algorithms. Next week, we will then use these kernel transformations or these kernel functions to link that with a quantum mechanical implementation of support vector machines. But as I said, support vector machines are extremely flexible. They are very popular. And for data sets which are not too large, which means data sets which can be handled by linear algebra problems together with optimization types of problems, then the support vector machines offer a very flexible machine learning method. And these methods belong to what are normally called the pre-deep learning revolution methods. So support vector machines were actually introduced back in the 90s of the previous millennium, whereas deep learning methods like neural networks, convolutional neural networks, although they have been developed decades before, they really took off around 2010. And we normally tend to call that the deep learning revolution time, or whatever we might call it. Now, the thing which is important for us now is that since we have a constraint, this leads immediately to a formulation in terms of Lagrangians. So if you look at this simple case which we had before the break, you could now think of this x1 here as being something which gives a more general constraint of g of x, where now x is a function of both x1 and x2, or it can contain more variables. But g of 1 is a function which now represents the first constraint. And this is something which then could have a specific value. It could have a value of b of 1, for instance. Or it could be larger or equal than b of 1. Then we could generalize this one to g of 2 of x equal to a value of b of 2, etc. So we could continue if we have, let's say, more variables like x1, x2, x3, up to a given xm. We could then think of just adding more constraints. So we could have a function of g of m of x equal to some variable b of m. This means that we could define a Lagrangian, which is a function of these x's, and then a function of these parameters lambda, which are called the Lagrangian multipliers. And these are parameters which we now have to add because the variables are no longer independent. So if you think of the problem here without a constraint, just this one, then we would say that x1 and x2 would be independent of each other. But as soon as we put a constraint here, then not all variables can be independent. And that leads to the whole machinery of Lagrangian multipliers. And if you go to the Jupyter notebook and in also the PDF file, you will find a quick reminder on Lagrangian multipliers. So this would then in general be given by the function f of x. And then we have minus, and then there will be a Lagrangian multiplier for the first function, g1 of x minus b1. We would have minus lambda 2 of g2 of x minus b2. And then depending on how many variables we have, we could end up with a minus lambda of m of g of m of x minus b of m here. And these parameters lambda 1, lambda 2, up to lambda n, they are normally called Lagrangian multipliers. And I am actually assuming that you probably have seen this formalism in different mathematics courses. So what we would do then, in the optimization part, we would then find the gradient with respect to the x's, x of I equals 0. And these x of i's, they take variables from 0, 1, up to some n minus 1. And similarly, we would also take the derivatives with respect to lambda of j. So this should be a lambda. Let me just write that in a better way. And this will be for j equal 1, 2, all the way up to n. So these are then the Lagrangian multipliers. And one way to see this is actually through another example. So let's take a look at a new example. So example 2 here. You probably didn't get time to write everything. So let me just keep that one before I dive into the second example. So a second example here is again a two-dimensional case, which we can solve easily by plane derivations and find the parameters which for the Lagrangian multipliers. So if we look at this example where I'm going to set x1, x2 equal to a pretty simple function, it's just a straight line of x1 and x2. And this is subject to the constraint that x1 squared plus x2 squared is equal to 10. So what it means then, if we now make a plot here, so this is square root of 10. So the x1 squared plus x2 squared is then going to define a circle. And then we have 1, minus 2, minus 1, 1, 2, 1, 2 here, minus 1, minus 2. So we have a circle which intersects the x and the x1 and the x2 axes. So we have x1, and then we have x2 here. And then we have the straight line, which then intersects somewhere here. So this is not very, how to say, it's not an optimal figure, but I hope you can accept my lack of drawing capabilities here. So this is a straight line, and these are the points which we want to find. So when we then calculate the derivatives, we can now set up the derivative with respect to x1, and that gives us 1 minus 2 of lambda of x1, and we want that one to be 0. So the Lagrangian in this case is actually going to be given by x1 plus 3x2 minus, and then we have the parameter lambda, and then we have x1 squared plus x2 squared minus 10. And this is the function whose derivatives we are actually going to calculate. So if I do this one, I find that x1 is equal to lambda divided by 2. If I do the same thing with x2 here, that is going to give us that x2 is 3/2 times lambda. And then finally, I need to take the derivative with respect to lambda and put that one to 0. And that is going to give me, obviously, that x1 plus x2 squared is equal to 10. And if I then use these relations which I have, I will then find the following. I will then find that lambda is equal to plus minus 1/2. So I will get two cases where lambda is equal to 1/2 and x is equal to 1. and x2 is equal to 3. And then I have the second case, which is the other point, when lambda is equal to -1/2, and x is equal to -1. And finally, when we have x2 is equal to -3. So we can have different types of expressing these constraints. So when we have the constraint, which we had in this particular case, then we would say that the constraint is active. So that means that when this g of x is exactly equal to 0, what we find in this particular case is that lambda is equal to ±1/2 for this specific example. And we say then that the constraint is active. When the constraint is not active, then we could have a constraint of the type that this should be larger than 10. That would be an example of what is normally called an inactive constraint. And in that particular case, the constraint which we have doesn't play any role. And in the optimization, in order to find the stationary points, then it suffices just to take the gradient of the function f of x, which we want to optimize. And that means that we can put lambda equal to 0. Because in that case, when we put something like that, it means that the constraint is no longer active in the optimization problem. And you can see that immediately if you look at the next example. So in this particular example, we could now set up a function of x1 and x2, which is now given by 1 minus x1 squared minus x2 squared. And then we could have a constraint subject to g of x1 of x2 equal to x1 minus 1. Now, if I plot the function now, it's going to look like this. So our function will now take values depending on x1 and x2 here, where we can have different circles. Now, the constraint which we have is now just a straight line, which will be something like this. And we see that for this specific point which we have here, then if we label this point x star, then this contains now an x1 star and an x2 star here. This will be the case where the constraint is active. So that means that what we have is that the g of x is equal to 0. So the constraint is active because we require that we actually, the line here hits the function f of x1 or x of 2 here. But when so that means that when the solution is on the boundary, in this specific case, we have lambda different from 0. So we call this an active constraint. When g of x is, say, larger than 0, then it doesn't play any role. And then we say that the constraint is inactive. So if we have an inactive constraint, this means that g of x is larger than 0. And in that specific case, then the only thing which suffices is actually to calculate d of f of x with respect to x and put that one to 0. And we can then have lambda equal to 0. So for either case, however, what we have is that lambda times g of x is equal to 0. So when it's active, then g of x is equal to 0 and lambda is different from 0. And when it's inactive, then g of x is larger than 0 and lambda is equal to 0. So what we are going to do then is to perform an optimization. So we optimize with respect to a function L, the Lagrangian, this doesn't make sense. We optimize a Lagrangian with respect to x and lambda, subject to the constraints. And let's just write them down here. So g of x larger or equal than 0. And we can have an active case and an inactive case. Lambda is normally set to larger or equal than 0. And then we have that lambda times g of x is equal to 0. So if we now look at these support vector machines, so what we are going to do now with a support vector machine with a margin is to optimize a problem which is given by this unknown vector w. We are going to minimize its norm, which corresponds to maximize the margin. So the support vector machine, then the basic recipe is a minimization problem of w and w0. And then I'm going to put a half here, because then when we calculate the derivatives, we get rid of the factor of 2. It's because we have a factor of half in front of it. So we're going to optimize the norm. So minimize, subject to a condition here where we have the output values we want to reproduce. And we have this vector w multiplied with x of I. And remember that x of I can be a vector. And this one is equal to 1 for all I, all the observations which we have, the data points, up to n minus 1. So the kind of Lagrangian which we are setting up then is the following. So we have this 1/2 of omega of transpose times omega. This is the quantity we want to optimize, but then we have a constraint, and we are going to write this constraint as we would set up the standard Lagrangian multipliers. And now for all the data points which we have, so we have a Lagrangian multiplier, and this is then multiplied with a constraint, y of I, and wt of x of I plus w0. And then there's a parenthesis and minus 1. And finally, the final parenthesis. This is the problem we want to optimize in order to find this marginal vector or support vector. So if I now set up the derivatives, I set up the derivative with respect to w0, and that gives me minus of y of I of lambda y. That is one of the derivatives. And then I'm going to set up the remaining derivatives, just keeping in mind that the x now is a vector or can be a vector. So if you have only one parameter for w here, then clearly w and xi are just two scalar numbers. But in general, w is a vector and x of I is a vector. So the next derivative which we need to look at is now my d of L of d of w. And I'm going to calculate the derivative with respect to the transpose here. And that is going to give me minus, sorry, not that one. I will get a w minus, and then I have a sum over I, 0 up to n minus 1 of lambda of I, of y of I, multiplied with x of I. And just keep in mind that this x of I can be a vector. And finally, I have my derivatives with respect to lambda of I. And that one is also something I want to drive to 0. And that gives me y of I, W transposed, plus W0 minus 1. So what we see now is that from this equation that W is equal to a sum of I, lambda of I, y of I, x of I. So I can insert this back in the equation, insert in L again. And then I can rewrite my L, since I've used one of these equations to simplify. And you see now that when I insert this one, I will get an expression which runs like this. There's a sum from I equals 0 to n minus 1 of lambda of I. This is the term which, when we go back a little bit here, when you look at the terms here, there's going to be a lambda of I multiplied with 1 here, minus 1 and plus 1. So that term is something which we can isolate, and that gives us this term. Then, since I am multiplying with the term for W, which I have found now, so the W's, I'm inserting W here, and I'm also inserting W here. So that means that I am inserting this expression inside the double sum, but also in here. So this gives me a factor of a half. And when I set it up, there's going to be a factor of 1 here. So when I bring everything together, this is just going to give us minus 1/2. And this will be a double sum of I and j. I'm going to have a lambda I, a lambda j, a y of I, and a y of j multiplied. And keep in mind now that these are vectors. So I have to have x of I transposed times x of j. And this is subject to lambda of I larger equal than 0, and the sum lambda of I, y of I equal to 0, which follows from the equation which we have here, from this equation. And so let's just put the final one. And obviously, we have to plug in lambda of I multiplied with y of I times wt x of I plus w0 minus 1. And that one is something which has to be when we take the derivative with respect to lambda, we have a constraint here. So if you look at this specific constraint, then we have when we take away lambda. So let's just, sorry, this should not be here. This is the final constraint which we have. So lambda I has to be larger and equal than 0. This equation here has to be fulfilled, and this equation here has to be fulfilled. In the literature, these are called the KKT relations, where the two Ks stand for kosher, and let me see if I remember the other K guy here. So these are called I always forget one of the Ks. Let me see, where did I put it? The kosher, Kuhn, and Trocker conditions. So x of I is then on the boundary, and that defines the margin, and that defines the so-called support vector. So the x of I, which we have here, that defines what is normally called the support vectors, because we can also now, from this relation which you see here, from this relation, we can then define the values, because we have wy times wt of x of I plus w0 is equal to 1. And from that one, I can then find w0 equal to 1 over y of I minus wt of x of I. So we can now rewrite this in terms of a matrix. So I can define a vector now, lambda of t, which is given by lambda 0, lambda 1, up to lambda n minus 1. And then I have my y of t, which is given by y0, y1, up to y of n minus 1. And if you look at the equations which we had for the final Lagrangian, we can actually set this up now in terms of matrices, and that allows us to set up everything in terms of very useful softwares like convex optimization software problems. So we can rewrite everything which we have here, this term and that term, in terms of a matrix problem with constraints. So if we now introduce these vectors, the first term which we have, that means this term here, can then be written out as an identity matrix times the lambda values. So that means that if we now set up the Lagrangian here, I can rewrite it in terms of a matrix, the identity matrix, which has dimensionality n times n, multiplied with this vector lambda. And then I have minus, and I have a factor of a half. I take the transpose values of lambda, and then I can set up a matrix here where I have y0, y0, x0 transpose times x0. Remember that the x's are vectors. y0, y1, x0 transpose times x1. And this goes all the way up to y0, yn minus 1, x0 transpose, xn minus 1. And this continues obviously down to yn minus 1, y0, xn minus 1 transpose times x0, and all the way down to y of n minus 1, y of n minus 1. And then I have an x n minus 1 transpose times xn minus 1. And this is multiplied with the vector lambda. Subject to, this is our final optimization problem, that y transpose times lambda is equal to 0, plus the additional KKT conditions, which simply tells us that lambda y have to be larger than 0, and that y of I of wt x of I plus w0 minus 1 have to be equal to 0. So these are the conditions which we need to set up. It's pretty common to actually replace this kernel, which you see now, or these functions here, with a function k. So we can then replace x0, x0. In general, we have an x of I and an x of j with a function with a so-called kernel. Which now is going to be given by function k of x of I of x of j. And that means that we can now define a matrix, which I'm going to call for P. And that will now contain y0, y0, and then I have k of x0, x0, and that continues all the way up to y0, yn minus 1, and then I have my k of x0, xn minus 1, and this goes all the way down here to y of n minus 1, y of n minus 1, and k of xn minus 1, comma, xn minus 1. And this matrix here allows us now to rewrite. So we can then rewrite the Lagrangian as a function of these parameters lambda as 1, the identity matrix, times lambda minus 1/2 times lambda multiplied with this matrix lambda, now P times the vector lambda. Then it's common to actually rewrite this xi of xj in terms of functions, which we are going to call for x of I transposed times phi of x of I. And if we have a linear kernel, so these k's are called kernel functions. So if we have a linear kernel, then this phi of x of I is given by just x of I, as we have seen till now. Now, these kernels are quantities which will now allow us to make the transition to quantum support vector machines, where we now are going to express these kernels in terms of a quantum mechanical basis. This is going to be the topic for next week. So what I wanted to do now is actually, after we've gone through this machinery, is to go back to the Jupyter notebook, and we're going to look at some of the implementations which we can do with a standard machine learning library like scikit-learn. We are also going to discuss what is called a soft margin. So till now we have defined a hard margin, and this is defined when we find these parameters for W's and the subject to the specific constraints. Then we define these vectors which define the margin, and that is the information which we will keep when we are setting up the support vector machines. But let's now go back to the Jupyter notebook and look back at some of the things we have done, because you will find essentially the same information I went through on the whiteboard here in the Jupyter notebook as well. So let's just take a look at the Jupyter notebook. And let's go back a little bit. So the problem which we have defined till now is essentially a problem which runs like this. So we would have a Lagrangian when we took the derivatives now, when we set up the different derivatives. We have a Lagrangian which is now given in terms of these parameters, these Lagrange multipliers, and subject to these specific constraints. And then we have the so-called Karush-Kuhn-Tucker condition, which simply relates the constraint in this specific way. So if lambda of I is larger than 0, then this quantity is equal to 1, and we say that xi is on the boundary. If this one is larger than 1, then we say that xi is not on the boundary, and then we set lambda of I equal to 0. This goes back to what we discussed about the active constraints and the inactive constraints. So when lambda I is larger than 0, then these vectors, x of I, when this condition is fulfilled, they are called the support vectors. And they are the vector closest to the line or hyperplane that defines the margin n, which we discussed before the break. So with that information, then we can actually define the support vectors, and that is what is needed for us to be able to set up a classification problem. And as we said in the whiteboard, we can then define everything in terms of a matrix here, and then this will be subject to these specific constraints here. So the last step when we are solving the above problem is then to, when we have put in these specific vectors and set up the value of b, which then simply results into this, we can then write out in terms of the support vectors only, where ns is being the number of support vectors. So this is just a normalization factor. This is something which we then can set up in terms of this expression here. And that defines the support vectors. So with the classifier equations set up with the hyperplane coefficients, we can then use our classifier to assign any observation by simply using these parameters b we found and the parameters w which we have found. So there's another thing which we discussed before the break, and also there was a question during the break about what happens if we cannot separate classes perfectly well. So there can be misclassified points. So one way to deal with that is something which is called a soft classifier. So that means that we can then add an additional parameters which allows us to misclassify some of the points. So that means that instead of having rigorously 1, which we did, we can now say that there is a slack, which is called epsilon here. So we have 1 minus this epsilon. And with the requirement again that these epsilons are larger or equal to 0, and the total violation should not go to infinity, but it should exceed, when we sum it up here, it has a maximum value which we can set it to. So in this specific case, this value in the constraint in the last equation, that corresponds to the amount by which the prediction, which we have here, is on the wrong side of its margin. Hence, by bounding this sum, we bound the total amount by which predictions fall on the wrong side of the margins. So misclassifications occur when this one is larger than 1. And this bounding value, you can actually bound it by some value C, which then is a kind of bound for the total number of misclassifications. So when you use these machine learning libraries in support, let's say in scikit-learn for support vector machines, you will find a parameter which is called C typically, and that refers to the misclassification bound. That means that your Lagrangian problem now contains this misclassification. So instead of having 1, which leads to what's called a hard margin, we allow for a kind of slack. It's often called a slack parameter. And that means that we have a new parameter here. So we have new Lagrangian parameters, gamma y here. So that means that the derivatives, again, we have to set up derivatives with respect to the bias, these weights which we have here as before, but then we need also to set up the constraints with respect to these slack parameters C. And that gives us a new set of equations which we need to set up. Now, there is a very nice case here, which also addresses the question which one of you raised during the break. So the slack parameter is a way to allow for some events being misclassified, but then we run into problems where the data set is not easy to separate well. So if you look into one of the programs which we have here, so this is a data set and we are using scikit-learn as a library. So we are importing from scikit-learn the support vector machine C here is for classifiers. So we are dealing with a classification problem. And in this case, I made a very simple data set where I just have a linear space. And then I make a transformation. So where my data are actually squared. And in my specific case, I have an array of data points where I either have zeros or ones. So if you now look at the original data set, which is 1 to the left here, you see now that if you think of separating the triangles from the squares, this looks almost like an impossible mission. Now, what we did here is actually to square the data set. When you square the data set, you see now that since the squares are actually for larger values in absolute value for x1s, we can then have values which can be easily separated. So this is an example of us performing a transformation of the data set, which means again that this function which we called here, if we go back a little bit, so in here we just have the x's, the transpose of the vector times the vector. We could now make this more general and look at this as a function which transforms our data sets. And this leads to this concept of a kernel. So that means that instead of having a standard multiplication of an x transpose with x, we could now think of having a transformation. So we could use a polynomial transformation of degree 2 if we want to. So you could continue to live in a plane with x and I, xi and yi as variables. So you could have something like this. So that means that what you're doing now is to have a new basis, and where the equations, and now I'm just leaving out this slack option, so I'm having a hard margin again. So you could now think of transforming your x's in terms of this function c here, where now this z is simply given by this function here. And if you now look at something which runs like this, so this should actually be, no, there shouldn't be, I shouldn't have a y here. There should be an xj, sorry, this should be different. This is a small typo here. But I could actually set this up in terms of such a transformation like this one. So you can actually set this up in terms of these kernels. There's something which is called the kernel trick, which we are not going to look at now. The most important thing is that we can actually perform a transformation. And this is the property which we will use when we are going to move into quantum support vector machines. And this is where we will start next week. So the problem to solve now is a problem where we have transformed the data in terms of this kernel here, which acts on the x's. And then our matrix now takes this form which you see here. So the optimization problem, which we have, is something which we can rewrite in a more general way. So we have an identity matrix times lambda. So we could rewrite this in terms of some vector q of t times lambda. And then we have lambda transpose times this matrix P, which is now this specific matrix. And this is subject to some constraint where we have some G times a lambda here, smaller than some H. And then there could be another constraint as well. And let's see how this can actually be set up. So typically what we have, P is the matrix, which now has these matrix elements. And with given a given kernel and these targets values, y of I, this is the output, this matrix is pretty easy to set up. And then the constraint, y transpose times lambda equal to 0, that leads to this function f being equal to 0, which we have here. And this a is equal to y here. So that means that what you have set up here is that a times lambda is actually equal to y transpose times lambda. Then how to set up this g is something which we will discuss a little bit later. But we just note that these inequalities require that these lambdas are less than a specific value. And that can be split into lambda larger than equal than 0 and lambda y less than equal than c. And these two equalities then define the matrix G and this vector H. And there is a software which is called convex optimization, or CVX opt, which is a library you can include in Python code and actually solve this type of optimization problem. Now, these kernels, and one of the reasons why these often are called exponential kernels, is that a very popular kernel is actually based on a Gaussian basis functions, and it looks like this. But you can have just a linear one, like the one which we put up before. You can have a polynomial one, where polynomial to a given degree. You can have a tan hyperbolicus if you want to, and there are many, many others of these type of kernels. So next week, we will elaborate a little bit more on the kernels. And if you scroll down here, if we now just leave out this code here, which now shows the different types of examples on how you can set up the margins and the slack parameter in order to find the best possible way to distinguish between the different classes. You can see now this is a case where we have now a margin and slack parameters which are fixed, and you can then separate well or separate badly the classes which are dealing with. When you now look at the optimization problem, which we have, it's us optimizing this problem and subject to these constraints here. The typical way you would solve is to use a function which is called a library, which is actually called convex optimization, which is something you can easily include. So you would just have a pip install and write the name of the library. And in our case, if you now look at an example, suppose this is the case you want to solve. So this is the function we want to optimize, which is then, so we have something which we can rewrite in terms of matrices. So if you look at this function here, we can now rewrite it in terms of this vector here times this matrix times a vector times a vector again, which would be the first term. And this could be subject to x and y larger or equal than 0. X plus 3y larger than 15. This is just an example which is being set up. And you can then rewrite these similarities in different ways. But one of the ways you could do this now is simply to set up all these constraints which you have in terms of a matrix, which is this matrix here, which will be the matrix G. And you have a vector H, which is then given by the values which you have here. 0, 15, 180. And you see now that if you invert it to 0, minus 15. So this is minus 15 because this is larger or equal than. This is less than equal, so you just invert it here. So then you have a minus 15. And then, so you just collapse all the inequalities into a matrix G. Also the matrix P, which is more complex when you do a support vector machine, is much simpler in this case. And then you would simply then set up the matrix here. And this is the way you would simply set it up. You need to set up the diagonal. You have the matrix P, Q, G, and H. And then you construct the matrices. You involve the solver. And then you can find the solution here. And then the solution would actually be the one which you see along here. And then this is the optimal solution at the end. So to anticipate a little bit what is going to come here is the quantum support vector machines. So the idea of a classical support vector machine is that we have a set of points that are in either one group or another one. And we want to find a line that separates these two groups. And this line can be linear, but it can also be much more complex, which then can be achieved by the use of these kernels. We will then translate, we will have to translate the classical data points into a quantum data point. And this can be achieved by a circuit, which we will discuss next week. So let me just bring back because the Jupyter notebook didn't render this properly. So let me just bring back so not that one. Okay, it seems I put my, now let me just bring back the Jupyter notebook. And this is, why doesn't it share properly here? Okay, here it comes. Sorry for that. So we are going to need an ansatz where we are going to find a parameterized quantum circuit that processes the data in a way that in the end we can apply a measurement that returns a classical value of -1 or +1 for each classical input that then identifies the label of the classical data. So next week, we are going to look at, and these slides are better viewed in the PDF file. So the Jupyter notebook didn't render properly the mathematics here. I'm going to fix that one for next time. But then the plans which we are going to have then, if we now scroll down, is that for next week, we are going to discuss the quantum support vector machines and also quantum kernels. And then if we get time, we will then introduce quantum neural networks. However, a general introduction to standard classical classical support vector machines is needed, because what we are going to do now is to change these kernels and introduce quantum mechanical states and look at how we can then define a quantum kernel instead of a classical kernel, where the classical kernels, the most used ones, if we go back to the type of list which we set up earlier here, if we just scroll back a little bit. So the typical kernels which are used in machine learning implementations of support vector machines are given by typically the Gaussian type of kernels. These are some of the most popular ones. And people would, in order to make a classification problem, you can also do regression type of problems. These type of kernels become an additional parameters in the optimization. And since the case which you saw here, this one is normally not the typical case. You normally have a multi-dimensional surface, and then it's not so easy to see what kind of kernel is appropriate. It's pretty common to play around with different types of kernels. So with this kind of background to classical support vector machines, we are now ready to jump into the implementation of quantum support vector machines. Now, in our applications, we are, for those of you who want to do this as project number 2, we would typically recommend that you use either Penny Lane as a software or Qiskit as a software in order to implement quantum support vector machines. So I'm going to stop here now, and we see each other next week. I'm going to stop the recording here.